to welcome Professor Simon Blackmore. He's the Director of the National Centre for Precision Farming.
Okay, well, thank you very much for the introduction. I realise that, in fact, obviously, most of you are robotic engineers and technicians and academics. So, in fact, some of this is going to be a bit of a crash course in agriculture for you. Because although I, like you, am very interested in what robots can do for us, I'm coming at it not necessarily from a robotic point of view. I'm coming at it from an agricultural point of view, and so I've got the application area. And I'm then going to show you some of the problems that we've got and maybe even some of the solutions. So my presentation is a little bit longer than the 15 minutes, so I will have to skip over some of these things. But recently I've been doing a lot of talks about projecting this into the future. What's farming going to be like? But if I just try and keep to the essence of the messages I'm trying to give here, that automation and robotics will play an important part in conjunction with other areas so that we end up with a new mechanization system. And I would suggest that the current farming system is based very much towards production, as are the machines that then help us do this. And we then have to move towards flexible manufacturing, as most other industries are doing. And a lot of our research has been geared up towards the ability of, or the opportunity to do real-time management, dealing with the current conditions rather than always trying to deal with averages. I'm an agriculture engineer. I like the big tractors, but the big tractors can have problems. And one of the lessons that we've then learnt is that we cannot change the weather, but we can change the tractor. Most people will be aware we've had a very wet winter time, and the machines that then we use to go and put seed into the ground cannot go into the fields yet because the soil is so soft. And that's what we actually end up with. And the problem is, it's not necessarily size is the problem, it's weight is the problem. Every kilonewton in the horizontal direction, we need another kilonewton in the vertical direction. And it's that's causing this problem. So the farmers are all blaming the weather. We can't do anything about the weather. I'm now blaming the tractors. We design the tractors, we build the tractors, and it is the tractors that are causing the problem. And so therefore, we've got to come up with something different. And there's a whole range of other factors of why I think we should change the agricultural mechanization. So I worked with Massey Ferguson to develop some concepts. Rather than trying to explain these things, I used the graphics then to be able to have it as a discussion document to be able to show some of these ideas. And in fact, okay, thank you. In fact, if we are then going to use these machines, then how will they fit into the rest of the system? And in fact, what the assumptions I'm making is that we don't need to change many other things to be able to get these big advantages. But we've got to come back to removing the machine constraints that we've got at the moment and get back to focusing on the plant needs. And we need management information systems plus the technology to be able to do this. But it will also retain the requirement for the big tractors, and people are obviously in this system. But the robotic system would then perhaps reduce down to 4 stages: crop establishment, crop scouting, crop care, and selective harvesting. So if we then move away from the big tractor that sinks into the ground to something that is then a lot smaller and lighter, every little seed that we put into the ground is just a tiny little thing. We need then a cubic centimeter around it to be able to give the correct environment for the seed. Then we don't need such a big machine. We can do the same sort of things with something that's a lot smaller. So it's got to be ultra light, very low draft force, no agronomic compaction, put seed into the ground in any weather. That's what the farmers want. And then we're coming up with concepts such as micro-tillage, cultivation for each individual seed position, permanent planting positions for the seeds, and then use different techniques, vertical or rotary seeding methods, and then being able to put seed into the correct depth according to the moisture regime. And so here I put this as a challenge to my MN students this year to have less than 40 kilopascals or 6 psi underneath the contact patch of a vehicle. So they went out and bought a little lawn tractor here with four-wheel steer. They've got it underneath, or they've got it under radio control at the moment, but we're just putting it under SAFAR, Software Architecture for Agricultural Robots, which is the behavioral approach that have been developing over the last 12 years. And if you look on the right there, it's a little bit difficult to see. You might be able to see down here a little patch of water. That's where somebody stood and has compacted the soil so that it then retains water on the top. And of course, again, that's not what we want. We want the water to go down into the soil. But right beside it, there is a tire track. And so it's that light that it hasn't actually caused any compaction. And so here then we've got a machine that can go out and do something useful for us right at the moment and actually do it in a significantly better way than the current systems. Again, down the bottom here, you can maybe see some compaction, which then causes problems. Up to 90% of the energy going into cultivation is there to repair the damage caused by the machines in the first place. Significant opportunities to do things in different ways. Up to 96% of the field area is compacted by tires, by random traffic systems. When the tractors are moving around across the field, they are always then compacting the soil, and that is then causing problems. And if we don't damage the soil in the first place, then we don't need to repair it. The natural flora and fauna within the soil will actually then create the good environment for us. And so we've talked already of route planning. Paul's saying he's doing it without GPS. I think that is an excellent approach, and I agree entirely that we should make our machines smart enough to deal with the natural environment. But in agriculture, for many years, we've been doing the exact opposite. We modify the environment to suit the machines. That's why we've got the big fields and the flat fields and so on. But we do use RTK GPS, which gives us 2 centimetre level accuracy, and that is a significant benefit for us. And when I was heading up the European Future Farm project a couple of years ago, we were developing different tools and techniques for robotics. And we then came up with a way to be able to use Google Earth and to be able to click around the outside of the field, tell it the size of the tractor and the working width. It can come up with an automated route plan for us. But in fact, we're now using this more for manned machines to be able to guide manned machines. You might not be aware, in agriculture, we've been using auto steer for the last 10 years. It's hands-off driving for tractors. There's still a person on there. We have a joke in this area. How many people does it take to run a robotic tractor? You need a man and a dog. What's the man there for? The man's there to feed the dog. What's the dog there for? To bite the man in case he touches any of the buttons. So we do have people on the tractors, but more and more automation is coming in. But there is an interesting dilemma here. We can automate all of this. When we've had the students doing the development, okay, does it work? Yes. What do you want? How can we improve it? Please give me a desk so I can put my book on there. Meaning that they're not involved with the task that the machine is carrying out. We've disassociated with them completely. And so what level is the correct interaction? That's the sort of questions we need to then work out. We then are considering different machines to do crop scouting, unmanned ground vehicles, unmanned aerial vehicles are both options for us. And again, it's working alongside people. It's to be able to give people more information for the agronomist to be able to make better decisions. The concept of real-time management information system is really important. Here's one I made earlier. This one is the Dionysus robot for going out into vineyards. That's going to go to the University of Athens in Greece, and that'll carry then different sensors on it, thermal cameras for irrigation status, and multispectral cameras for nutrient status of the vines. And then we, again, like Paul's doing, we're using LiDAR for canopy measurement. It's giving us the canopy extent and also the canopy density. And this is actually very useful agronomic information for us. UAVs, very interesting area, moving ahead very quickly now. We just see these as skyhooks for carrying instruments, all range of different instruments, getting them small enough and light enough. On the left here, then, we're using our 3D printer to see how small we can make these and how cheap we can make them. And in fact, where it is then just a few centimeters across, we can put these into animal housing so that we can fly up and down inside the animal housing to be able to stream video and thermal imagery. Robotic weeding. Japan likes robots. This is my only anthropomorphic robot, which then is an exoskeleton, which was developed because of the aging population. But notice the date here. In 2006, I developed the autonomous tractor with a side shift system on there and the cycloid weed hoe. We know the position of every plant that goes into the ground because we put the seed there in the first place. 100,000 seeds per hectare. It's not a problem. It was an old 486 laptop that did the logging. So we don't need the supercomputing power. But what it's doing is that we know the position of every seed, and we're then withdrawing the mechanical leg so that we don't dig up the crop plant. It's a little bit too close. It's disturbing some of the weeds, but that's just a case of fine-tuning. This is the latest semi-commercial robot. Some of my old students in Denmark got together and have developed the Roboti here. Very little intelligence in this machine. This is just GPS controlled. But we do then have the ability to come up with object avoidance and different safety systems. But that's the sort of thing that we might be seeing in the near future. We've then got microdot spraying. Again, one of the PhD students in Denmark is explaining we've got a token weed here. We then will use machine vision to be able to recognize up to 26 different species of weeds. We know the location, the leaf area, the biomass, and we can then do different things with it. And the camera is then looking down underneath, and that device there is a little mini spray boom, which then will only be able to, or we can then just put spray only onto the leaf of the weeds, which then gives us quite an interesting statistic of 99.9% reduction of chemical by volume. And by the time it's then gone through, we can then see that the chemical has only been applied onto the leaf of that weed. And that then has got significant implications for the use of chemicals in agriculture, apart from the economics of it. You might think that this would be opposed by the, in fact, you might be able to see, it doesn't work with the video. Okay, you can just see the blue blobs on there. That brings us on to laser weeding. We can use machine vision to recognize up to 26 different species of weeds. We can work out where the meristem is, the growing point. And if we heat that growing point up to 96 degrees C, the cell walls then rupture and that plant then becomes dormant. You might think that the agrochemical companies would be against this, but I can now tell you as of yesterday that it's being funded by Syngenta, one of the largest agrochemical companies, and they've realized that robotics is a game changer, is a world game changer for them. They're a chemical company, but when we're capable of doing this to be able to control weeds, they've had a Kodak moment. You're probably all aware of what happened with Kodak, and they don't want to go the same way. And so they're now investing huge amounts of money in developing this, a competing technology, because it gets around the whole problem of having all of these chemicals. And sorry?
Isn't that exactly the opposite of what Kodak did? Kodak just went,
Yes.
and are these guys investing in the world?
Yes.
So that's not what Kodak did with Kodak.
Sorry, okay, the opposite to Kodak, or where Kodak went wrong, because they went out of business and they didn't want a Kodak moment. And so we've got Agritech funding to be able to develop this, and they put a significant amount of money, private money, into developing this. Which then brings me to the last couple of slides, the concepts of selective harvesting. We go out and harvest vegetables and fruit, go away and grade it, and we can throw away up to 60% of these fruits and vegetables, because you and I demand that a lettuce is like this, that a lettuce isn't like this, and a lettuce isn't like this. We ought to change society, but we're not going to try and do that. And so what the companies are then doing is then being able to do selective harvesting. And so, but the trouble is, up to 60% of the harvested crop is not of saleable quality because of natural variability within the fields. Only harvest that part of the crop which has 100% saleable characteristics. And there's a whole range of different things that we can do there. But if we can then be able to only harvest that which is marketable quality, we can then be able to come back later on. And so here's my concept vehicle of selective harvesting, which then leaves behind the perfectly good lettuces that aren't big enough yet, because we can come back in a week's time and harvest those ones and then sell them. So in conclusion, is this the future? My talk is then talking about at some point in the future, but you've seen from the approaches and the videos that we've got that in fact this technology is a lot closer than many people will think. These concepts have been developed and initially researched. Not many of them are commercially available through lack of demand, but that lack of demand is really lack of awareness. The farming community is becoming aware of these opportunities, but we've got to be able to find ways of getting these into the marketplace sooner rather than later. And in fact, I think that the UK has got a very good opportunity to be able to take a lead in this area with a whole range of these technologies. But it's a case of getting them into the marketplace as soon as possible. Okay, thank you very much.